Hi, my name is Gábor Valasek and I'm going to present our work with Róbert on quick cone map generation on the GPU. First, I will give a quick overview on our main application domain per pixel displacement mapping, including our main motivation for our work. Then I will present our algorithm and its improvement. And finally, we will compare our results both in terms of generation times and rendering performance with brute force cone maps and relaxed cone maps. Traditional textures encode high-frequency variation of optical properties. For example, a textured pair of triangles can appear as if its BRDF corresponded to a stone wall. Heat maps offer the same facility, but in the geometric domain. Displacement mapping translates points on the coarse geometry, the two triangles in our example, along a normal direction. The magnitude of this displacement is stored in the height map shown on the top right corner. With an additional scale on the height map effect, we can make displacement go from subtle to drastic. The height map scale defines a displacement volume. In per pixel displacement mapping, we compute the intersection between our view rays and this volume and look for the height field ray intersection between these blue points for every pixel. The simplest algorithm to compute the intersection between the ray and the height field is linear search. By taking equally spaced samples along the ray, we look for the first change of signs and use a root refinement, for example, binary search, to zero on the exact intersection between the ray and the height field. Linear search may fail to find the first intersection between the ray and the height field. The intersection it finds may also depend on the current viewing position. Cone maps offer a more robust mean to compute the intersection. Cone maps store the widest unbounding cones for every texel. The axes of these cones coincide with the normals along which we do the displacement. Brute force cone map generation takes every other texel in the height map and computes the widest cone that is not intersecting the interior of the height field. Texels below the initial texel may be discarded, and texels that generate wider cones than the one we have so far may be also discarded. So in this particular example, when computing the cones from the blue texel, the first initial cone proved to be the widest unbounding cone that is not intersecting the height map geometry. This property allows us to employ efficient empty space skipping during rendering of a height field once we have converted it into cone maps. Cone maps are represented by two scalars at every texel. One encodes the height of the apex of the cone, and the other one is a function of the cone aperture function, usually the tangent of the half angle. The unbounding property of these cones allows us to proceed to the intersection between the ray and the cone at every iteration. Assuming that the current position along the ray is always on the axis of the current cone, we can make these intersection computations between the cone and the ray very efficient. We can terminate when we are very close to the surface. Cone maps by themselves won't allow the ray to enter the height field. Cone angles tend to become very narrow in valleys. This can slow down cone step mapping considerably. However, Poliparco and Oliveira noticed that cones can be widened without sacrificing robustness. As long as no view ray within the cone can intersect the height field more than once, we can use cone step mapping for rendering. We just have to make sure to do a proper root refinement after the initial trace, usually a binary search. Rendering with cone maps is the most efficient and robust way to display height maps. Unfortunately, generating cone maps usually relies on brute force algorithms. For n times n textures, this results in theta n to the fourth complexity, as we have to check for every texel, every other texel, and look for the smallest cone aperture. This means that not even a 1K texture can be computed or converted into a cone map within a single dispatch. And conversion of smaller resolution textures is also not feasible on a frame-to-frame basis. Our goal is to devise a n² log n algorithm to convert height maps into cone maps by using maximum MIP maps. Similarly to normal MIP map chains, maximum MIP maps take data from a 2x2 texel footprint. However, instead of using the average of these four values, we take the maximum. This allows us to have a conservative bound on the maximum height within a texel region. So instead of checking every other texel for our current one, we can use the maximum MIP maps to batch together a region of texels and use a single texture read to cover that entire area. This simplifies our algorithm in a sense. All we have to do is for each texel to compute the cone map is to iterate over the MIP levels, the maximum MIP levels, and on the current one, scan the 3x3 neighborhood of the texel, update cone apertures if necessary, and then proceed to the next MIP level. In an example, when we are on the lowest level, we just take the normal 3x3 neighborhood and compute the narrowest cone aperture. Then, instead of proceeding to the next neighbors on MIP level 0, we increase the MIP levels. You can see that partially we have covered the 3x3 neighborhood in the previous level, but we can compute cone apertures regardless. We assume that the height, the maximum height, is taken at the closest point of these MIP regions to our current MIP region. And then just proceed until we have covered the entirety of the height map. Unfortunately, this naive algorithm generates low-quality cone maps. The bottom left image shows a render with one. The explanation of the visual issues can be seen on the right. All pixels in magenta have not converged to an intersection within 32 cone step mapping steps. This is because texels on the boundary of multiple MIP levels possess extremely narrow cones, which slows down cone step mapping. The reason for this is that we assume that the maximum height of the texel is realized at the closest point of the texel region. Luckily, there is a very simple change that can improve the quality of the cone maps. All we have to do is to exclude the areas that we have checked on a lower MIP level from the foot point computation. By foot point, we mean the place where we assume the maximum height to be realized. On this figure, yellow denotes the previously visited areas. U is the initial location of our texel on MIP level 0, and I is the center of the texel that contains U in the current MIP level. The green dots are foot points from I, where we assume maximum locations once we have discarded the already visited parts. All that remains to be done is to transfer these foot points back to MIP level 0 locations to compute correct cone angles. Depending on the relative position of U within I's texel, we can discard a cut corner foot point, here one of the two in F1 on the top left, and use translation on the other ones. This resolves our main visual issues with the algorithm. Here's a comparison between the naive and the improved algorithm with 32 steps. The amount of non-converged pixels has decreased significantly as well. Even with the above improvements, cones are usually still narrower than that of the brute force method. We can improve on this by discarding conservativeness and use a more aggressive heuristic to compute the food point, such as the center of the taxa region of the current MIP level. In our experiments, this still yields a cone map that can be correctly refined by a single second step. That is, it rarely guides the rays inside the Haight field. The table below shows cone map generation times with our proposed algorithms in milliseconds on an AMD GPU. The total column aggregates both the quick cone map and the unoptimized maximum bitmap generation times. Comparing it with conservative and relaxed cone map generation algorithms, we can see the improvement. Similar trends can be seen on an NVIDIA 2600 laptop GPU. And in terms of render times, we have tested two different scenarios, one that uses 32 and another one that takes 200 cone step mapping steps. You can consider one as a real-time and another one as a more interactive scenario. On both GPUs, the difference in performance between our cone maps and brute force was small, yet brute force was more performant. Focusing on the comparison between our center heuristics and relaxed cone maps, we can see that low step count scenarios bring these two very close to each other. This is due to the fact that our center heuristic can use a linear or second root refinement search, whereas relaxed cone step mapping has to use binary search to avoid all visual artifacts. However, as we increase the iteration counts, our heuristic will fall behind in terms of performance. To sum it up, we have shown an algorithm that can convert height maps to cone maps very quickly on the GPU. Even a 4K texture took less than 10 milliseconds on the AMD GPU, while a 1K texture was converted in less than 0.5 milliseconds, including maximum bitmap generation. This makes per-frame cone map conversion viable. For best render performance in real-time setting, we suggest using the more aggressive center heuristic variant of our algorithm with the second root refinement step. Our source code is available on the link above, and I would like to thank you for your attention.